Let's pretend machine learning never existed. You and I still want the same thing. Look at what we know and make a good guess about what we don't. This episode is about the obstacle that forces everything else to exist. Prediction is hard, not because we're bad at math, but because the world is noisy and uncertain. Imagine a simple task. Predict tomorrow's temperature from today's. If the world were perfectly predictable, the same input would always give the same output. But in real life, the same today can lead to different tomorrow because of hidden variables we didn't measure. That's the first crack in the dream of perfect prediction. Let's make that concrete. Suppose X is today's temperature and Y is tomorrow's temperature. We observe many pairs. If you plot them, you don't see a perfect curve. You see a cloud. The cloud is not a failure of plotting. It's the signature that X does not contain all the information needed to pin down Y. So what does it even mean to predict Y from X? It can't mean guessing the one true Y, because there is no single Y. The honest goal is, given X, choose a number that will be close to the actual Y you'll see. But close is a judgment call. We need a definition of error. Let's zoom into a single X value. Think of X fixed at, say, 16 degrees today. Across many days, tomorrow's temperature Y varies. That variation is a distribution. Some outcomes are common, some rare. If we must output one number, we're really choosing a representative point of that distribution. Now we can ask a precise question. If I pick a guess G for this X, and reality draws a random Y from that distribution, what guess minimizes my average error? The phrase average error is doing a lot of work. Different error choices lead to different optimal guesses, even with the same data. Here's the key derivation, done visually. Imagine sliding your guess G left and right along the number line. Under squared error, being off by 2 hurts 4 times as much as being off by 1. That makes outliers matter more. The point where pushing G slightly left or right stops improving average squared error turns out to be the mean. Under absolute error, the story changes. Now being off by 2 is only twice as bad as being off by 1. Outliers don't dominate. When you slide G, the tipping point happens when there are as many samples to the left as to the right. That's the median. Same data, different definition of error, different best guess. This is the first principle that replaces magic. Prediction is not a single problem. It's a contract. You choose what errors you care about, then you choose the guess that minimizes the average error you expect to face. In symbols, we'll later write, pick a function that minimizes expected loss. But the idea is already here. So why is prediction hard? Because the same input can honestly lead to multiple outputs, and because best depends on how you score mistakes. In the next episode, we'll take the smallest possible step toward a real predictor. Instead of choosing one guess for one X, we'll choose a whole rule that maps any X to a guess, starting with the simplest shape, a line.